All right, this is problem 3 in chapter 11 on page 449. A V-belt sheave transmits 1,112 inch-pounds of torque. Let's see, to a 1 3/4 inch diameter shaft. Let's see, the sheave is made from ASTM Class 20 cast iron and has a hub length of 1 3/4 inches as well. So, how do they describe that? Cast iron, ASTM, Class 20 cast iron. Okay, and the problem statement is to design a key. In fact, I'll read that. For problems 1 through 4 and 7, which are all in the range that I assigned, determine the required key geometry, length, width, and height. Use SAE 1018 steel for the keys if a satisfactory design can be achieved. If not, use a higher strength material from table 11.4. Unless otherwise stated, assume that the key material is the weakest link when compared with the shaft material or the mating elements. Okay, so when I worked this problem originally, I was working out of the 4th edition of the book instead of the 5th edition that we're using now. And the tables have changed just a little bit. There's a little more data for the cast iron materials that are included. So that modifies our analysis just a little bit. Now also, when I worked this problem before, I used 1020 cold drawn because in the problem statement it didn't say you had to use 1018. So I'll need some calculator help in order to get the right numbers. So pull out your calculators if you would, and let's see what we can do. Now the first step, which you've all probably discovered, is that there's a standard key size that goes with the shaft. So the key size standard is based on the shaft size. Since we have a shaft diameter of 1 3/4 inches, go to page 425, table 11.1. Will help you find out what size key is standard for this. So based on the diameter, the height and width, which will be equal, because this is a relatively small shaft, so you're going to use a square key. You don't use rectangular keys until you get into much higher shaft sizes. So anyway, let's see. In fact, you'll notice on table 11.1 there's a dividing line between the 5.5 and a 6.5 inch beginning shaft diameter for the cutoff there. Anyway, we're at 1 3/4 inches, so over 1 3/4 up to 2 1/4. And there's another option, 1.375 up to 1.75. So we have to decide which one we're going to use because we're right at that cutoff. Now let me see what I used before and I'll try to remember why I selected what I did. I chose 3/8. Now how I chose that that's right. Because it says over and then to and including. So notice that the line for 1.75 to 2.25 does not include 1.75. It has to be over 1.75, okay? So that's how I made the selection that the width and height, which will be same since it's square, will be 3/4 of an inch, 3/8 of an inch, which is 0.375, okay? So we'll start off designing a key like they wanted, and then we'll go and design a pin. All right, so we're going to, let's see, there's another page. Unfortunately, these are the old page numbers. There's another page that represents the safety factor, and I think it's in the text where he said what you use most of the time. The value is 3. Here it is. Page 429, design procedure for parallel keys. Step 3, it says, specify a suitable design factor in typical industrial applications. N equals 3 is adequate to accommodate accidental overloads and shocks. We don't have any reason to choose anything else, so I'll just choose a design factor of 3. Now, since we're told to use 1018 for the key material, so here's the hub, HUB, and here's the key. The key is 1018, so we need to go and look up properties for that. Now you could use 2 different properties. You could use yielding or you could use the ultimate strength. Which one do you think would make most sense? Yielding. I think yielding makes most sense because if the key is beginning to yield I don't know, I just wouldn't want it to break all the way, okay? So I think yielding makes the most sense. Although you could use the ultimate strength if you really wanted to.
Didn't you say last week or beginning of the week that picking up the slop or whatever?
Yeah, what I was talking about is if you use yielding as your failure criteria, then you guarantee that the hub and the shaft end up at the same angle, right? And if that alignment is really important, then it's probably important to go with yielding. Now, if we're talking about a hub on the bottom of a lawnmower or something, you know, and you just don't want it to shear off, maybe the ultimate strength makes sense then, okay? So anyway, a lot of times too what you'll find is you really don't need a very long key, and a practical length key has plenty of strength anyway. So unless you're trying to make it shear at a certain level. Now I've forgotten, they put a new table in the 5th edition. Here it is on page 428. Selection of materials used for keys. So the material designation they have there, the carbon steel 1018 SAE designation, has a tensile strength of 64 KSI and a yield strength of 54 KSI. So like I said, I'm going to use the yield strength of 54 KSI. Okay. Now, the yield strength, what is that? Do you remember from strength of materials?
The ones that wish the material no longer
Won't return, right? So it's permanently deformed. What else? What kind of load is that for?
tensile compression.
It's a tensile or compression load, right? Is that what we've got here? No, it's not. We have a shear load, right? And so what we have to do is figure out the yield strength in shear. Okay? So half is what we normally use. So if you take the yield strength and divide it by 2, and really what I'm going to do is I'm going to go ahead and calculate a design stress that's allowable. So not only will I take the yield strength over 2 for the sake of converting to a yield stress, I'm also going to divide by the safety factor n all at once. Does that make sense? Okay, so 54,000 divided by 2 and divided by 3. If you have your calculators, just take 45. Dyslexia for Kier Fallon. Sorry. 54 KSI, there we go. All right, so 54,000 divided by 6 is what? 90,000? 9,000, okay. So 9,000 PSI will be the design strength that we'll use. Now, we have to consider a few other things. First of all, we're told that this is a cast iron, which is class 20, and we've got this key that has not really a super high strength for steel, but you know, a reasonable strength. And you have to stop and think what's going to fail first. Well, there's a couple different failure modes for keys. If my hands represent a square key that's trying to be sheared and it shears off, that's one failure mode, right? If that whole plane fails. Another thing that can happen is the side face can be squashed in, right? So if you got your key, either the lower face or the upper half face could be squashed in, and that's a compressive type of failure. Now, in your book, page 428 and 429, I want to point this out again. Equation 11.2 and 11.4 are minimum lengths required for shear and compression respectively, okay? So if you're trying to calculate the size of key based on a shear failure, then that's equation 11.2. If you're trying to calculate the length of key based on compressive stress, a compressive failure, well then that is 11.4. Now if it turns out that the key is the weaker material versus the hub and shaft and key, if the key is the weakest material, then those two equations end up being exactly the same, and that's 11.5. In our case, we have cast iron and a key, so we have to go look up the strength, okay, and decide what's the weak link here. What is the weakest material? I thought I saw a hand back there a minute ago. You got it? Okay. Yeah, if you have questions, please feel free to ask. All right, so let's go look up cast iron and see what strength it has. It's in the back of your book in the material properties. Page 732 will do. And you'll notice that the very first entry in the table is the one we seek. It's gray cast iron, ASTM A48, grade 20. 20 just means that it's got an ultimate strength of 20 KSI. And now they have a new column here that they did not have in the 4th edition. In fact, they got a couple new columns. They have the ultimate compressive strength. Okay, it's labeled SUC. So because cast iron is a brittle material, its strength when you pull it apart is different than its strength when you squish it together, right? Which makes sense. So they've got this number here, but they've got a note on it. Note 1, approximate values, not part of the standards. If critical, negotiate with supplier. In other words, if you buy gray iron from supplier A, this grade 20, it's definitely going to have 20 KSI at least tensile strength. But its compressive strength won't necessarily be 80 KSI. Does that make sense? So we can't necessarily rely on that. Okay, now notice they don't have a yield strength. Why don't they have a yield strength here? It's too brittle. It doesn't yield, right? It just snaps eventually. Okay. Now, we have to make an engineering call here because we've got two data points. One of them says that the cast iron is 80 KSI, which is stronger than the key. The other one says the cast iron is 20 KSI, which is not as strong as the key. Which one do you think we should use? We could split the difference if we really wanted to and go for 50 KSI. Right? Is that right? 50? Yeah, 50 KSI. Wouldn't you use compressive? Well, we've got a problem. It is a compressive type of load, absolutely. However, we're not guaranteed that 80 KSI, right? What if the supplier gives it to us and its strength is 30 KSI? Then our analysis is shot, okay? We have to make a choice. What I did is I chose to use the 20 KSI strength. That way I could go through, and that's actually why I assigned this problem in the first place, was because I wanted to force you guys to use something other than just equation 11.5. I wanted you to see what would happen when you had a key that was the stronger material, which is a bad design, okay, but I wanted to force you to use some of the other equations. So anyway, so let's start with equation 11.2. The minimum length, in order to prevent shearing of the key, is 2 times the torque applied divided by the design shear stress divided by the diameter of the shaft divided by the width of the key. Okay, so this is page 428, equation 11.2. So 2 times the torque is 1,112 inch-pounds force. The shear strength that we're going to allow, the design shear strength, is 9,000 PSI, or pounds force per square inch. The diameter of the shaft is 1 3/4 inches, and then the width of the key is 3/8. And I'm off the video a little bit, so let me put it here, 0.375 inches. Okay, so let's see what units we end up with. We've got pounds force canceling nicely. Inches squared cancel with inches squared, so we'll just have inches of length. So like I said, I didn't run through these exact numbers, so please grab your calculator and give me a number here. So 2 times 1,112 divided by 9,000 divided by 1.75 divided by 0.375 comes up to what?
0.377.
0.377. Sounds reasonable. Anyone second that? All right, we got a second. So a little more than 3/8 of an inch would be the required length in order to prevent the key from shearing, okay? Now let's use equation 11.4 and figure out the minimum length of the key for compression. All right, so let's see, minimum length for compression. So this is shearing. Compression. The minimum length, L min, is 4 times the torque divided by, notice there's a different symbol here. What's different here? Stress is different, isn't it? We're supposed to use a normal stress here. We didn't calculate a normal design stress, we calculated a shear design stress. So how should we calculate this? What should we do? Well, to get the design stress, we decided that we're going to use 20,000 PSI for the strength of the cast iron, right? Now understand, I'm not talking about failure of the key, I'm talking about failure of the hub itself, right? Probably the shaft wouldn't be made out of cast iron. That would be kind of crazy. I don't think I've ever seen a shaft made out of it. Well, no, that's not true. A crankshaft in your car is usually cast iron, isn't it? But it's usually ductile cast iron, not brittle cast iron. Anyway, so what I'm going to do, it wouldn't make sense to plug in the yield strength divided by the safety factor, right? That wouldn't make any sense at all, because I'm not talking about failure of this key material, not of this 1018. I'm talking about failure of this cast iron instead, which I'm assuming is weaker. So what I'm gonna do is use the 20,000 PSI compressive maximum load, I'm assuming, divided by the design factor. Does that make sense? So I'm taking the not the yield strength, but the ultimate strength of it divided by 3. So 20,000 divided by 3, I can do that. That's 6,667 or so PSI, right? Notice here in the shear, we're using the width of the key because that's the important dimension, right? Whereas here we're using the height because we're talking about, if you've got your key there, at upper half and lower half, and you're pushing on the side of it, then it's the height that the pressure is distributed over, or the force is distributed over. So let's plug in everything. 4 times T 1,112 inch-pound force divided by, let's see, 6,667 pounds force per square inch, 1.75 inches, and then a height. Since it's square, it ends up being the same, 0.375 inches. Again, the inches, square inches cancel, the pounds cancel, and we end up with inches of key length. So if you plug this in, please, 4 times 1,112 divided by 6,667 divided by 1.75 divided by 3/8. Yes, sir.
Where'd you get the 20,000?
The 20,000, that's from the back of the book, the properties for the cast iron. It's, let me find the page number for you.
732.
732, yeah, that's it. Page 732 at the very top, number 20A is grade 20 cast iron. So I got it from SU. Good question. All right, anybody have a number for me here?
1.02.
1.02?
Yep.
Okay, so we got a second line. So should we make it 1.02 inches or 0.377, and why? What happens if we make it 3/8 of an inch long? Will the key shear or compress? Kind of a trick question because you asked about the key, right? The key's not going to do anything, right? The hub will be the one that compresses because look, the hub needs a longer length, otherwise the cast iron on the hub is going to be compressed, right? Now, like I said, this is a bad idea, it's a bad design. You always want the key to be the weakest material. What would you do to make this right? Find some key material that's weaker than the cast iron, or get rid of the cast iron fully and put something else on there, okay? So now, are you going to specify a key of 1.202 inches? No, what would you do?
1.25 maybe.
Either that or just go with 1 3/8 or 3/4, right? Why not? Maybe there's a valid reason, I don't know. But as long as the key is more than this, we should be fine. Okay. Now, if there's a serious overload, you got to understand what's going to fail is the cast iron hub, right? If the overload's big enough, that's the weakest material. You can see that right here. And so that's what's going to fail first is the cast iron. But if we make it 1 3/4 inches long, then it's going to take a serious overload. Basically what we're doing by making it 1 3/4 inches long is we're really just upping the safety factor quite a bit, okay? Which if this was a design I would probably do because it would, the purpose of a key usually is to fail first because the machine components are more expensive. So anyway, questions on that, comments? Now that's not all there is to it. Another thing we can do is size a pin connection for this thing instead. So let's just go ahead and do that while we're at it. Let's see, page 434, equation 1119 is the one we'll use. Let's say we don't use a key, so we use a pin instead. Then the diameter of that pin is given as the square root of 4 times the torque divided by the diameter of the shaft divided by pi and divided by our design shear strength. So if we plug in the numbers and we get 4 times, let's see, the torque, 1,112 inch-pound force divided by 1.75 inches, pi, and then the strength, the shear strength we've got is 9,000 PSI. Bless you. And we've got to take the square root. So let's see, what would we have here? We've got inches squared. So we'd end up with inches of diameter. So So plug that into your calculator if you would please, and then we'll discuss this. Yes, sir.
Would you use the 9,000 or would you?
I'm gonna discuss that.
Okay, because that,
Yeah, good question.
Point three.
Point three? Anyone second that? It sounds reasonable.
Yep.
Okay. What's your critique about using that stress?
I said to use that for the N-3 for keys, not him.
Okay, all right, so that's one, I wasn't thinking about that, that's one thing. You usually do include some factor of safety, that's why your author has toss of D on it. If you wanted it to be a, strictly speaking, shear pin, a pin that shears at the desired load, then you're right, we couldn't use the 3, right? Instead, we'd have to use the full shear strength of the material if we wanted to shear at 1,112 inch-pounds. Then we'd have to use, what, 54,000 over 2? So 25, 26, 27,000 pounds force per square inch, is that right? So if we did that, now what size is it?
0.173.
173, okay. Can you buy a key at .173? Not very easily.
It's not 3/16.
3/16, 3/16 is close, so you probably specify 0.1875, because that would be 3/16. Okay, you could do that, and basically the key would shear at a little bit higher load, or would it? Thought you were going a different way with this. Would it shear?
No, review.
Would it yield? It would yield before it sheared, but let's say the load got up high enough to shear the key. Would the key be the thing that shears?
Probably with the shaft.
It depends. It depends a lot, because look, here's what's happening. When you design a pin like that, what you're doing is you're just putting a pin through a hub and through a shaft. And you're designing it to shear. This is based on a diameter, or this is calculated in diameter, assuming the failure mode is the pin shearing on either side. That's what's built into the equation, okay? But we already said the cast iron is the weak link, right? If the material of this pin is 1018, will it really shear? Well, the reason I said it depends is because it depends on how much hub you've got, right? Because the more hub you have, the more area there is holding the pin in place, right? And the more the force in the pin is going to be distributed throughout the hub. Now, would the hub likely deflect a little bit on the sides where the stress is really high? Yeah, probably. Okay. And probably this is not a very good design either. You always want the element holding the shaft and the hub together to be the weak link, even in this case. But what I was going to point out here is it depends on how far the pin extends and how big this hub is as to whether or not it's actually going to shear there, or you're going to have some type of compressive stress failure inside the hub. Okay? So that's something else to think about. Questions, comments? Keep knocking the cord on this camera. I'm afraid it's going to make the video shake. Turned off autofocus and now there's just shake. Questions, comments? All right.